My name is Ajay Raghavan. I'm a research area manager at PARC, formerly known as Xerox PARC, with a distinguished history of pioneering breakthrough technologies in personal computing. PARC today practices open innovation in a number of interdisciplinary research areas, collaborating with various commercial, academic, and government organizations. Clean energy technologies in particular is a strong area of interest today at PARC. In this particular project today, I would like to tell you about some major advances we made in next generation battery management systems, collaborating with LG Chem Power, which of course is an industry-leading battery systems supplier. Together we've been working under the ARPA-E program, which is all about solving the pain points of today's battery management systems today. At a high level, all of these challenges result from the uncertainty in trying to manage against all these different cell failure modes, which can range from electrolyte oxidation all the way down to internal cell defects. And in some of the worst cases, these can actually even lead to extreme thermal events such as fires. And of course, these are rare, but when they do happen, there's a lot of negative media attention, which results in setbacks for the energy industry at large. A lot of these issues can arguably be attributed to how we are managing batteries today using these weakly informative parameters, temperature, voltage, and current, oftentimes only for groups of cells rather than in every single cell. And so in a sense, you are operating blind when you're operating your energy storage system with these weakly informative parameters, which is often what is the cause of all these issues you see on the field in terms of range anxiety and certain arbitrary failures. And if somehow these failures are avoided, you get a sense that you're not really using the battery to its true performance capability limits and being a little conservative and over-engineered. So our approach to removing the blinders with today's battery management systems is to embed fiber optic sensors inside the battery cells to directly monitor internal cell state. A key component to making this happen is our low-cost fiber optic sensing readout that is really pushing the envelope in terms of how accurate you can monitor fiber optic sensors for a large pack of batteries. And we have successfully worked those with advanced algorithms that can map the internal cell state monitored by the fiber optic sensors in the cells directly to the battery management system and give it parameters that it can use for managing the battery, such as state of charge, state of health, state of power, and other state parameters. And working with LG Chem Power, we've been hoping to make this field deployable for BMS in xEVs, grid storage, and other advanced applications, and not just be a laboratory characterization tool. So 3 years into this ARPA-E project, we made very exciting advances, and I wanted to give you some glimpse into what we've achieved, but it's easy to forget how many risks we were faced with at the outset, especially in terms of trying to embed the sensors inside, being able to develop a low-cost system that can monitor a number of cells. That sentiment was captured nicely by a major battery OEM engineer who visited us recently at PARC because he was so excited by these results that we achieved. But he reminded us that when we were selected for the ARPA-E program 3 years back, when he read our ARPA-E project description, it sounded like something straight out of a science fiction novel. What I wanted to do next is show you a short video of how we went about turning what sounded like a science fiction story 3 years back in much closer to reality. What I'm going to do next is go directly into some of the details of what we've achieved. And what I'd like to start with is a quick one-on-one on how fiber optic sensors work, because this tends to be a relatively new animal for a lot of people in the battery industry. Fiber optic sensors that by themselves are not particularly new. They've been around for 2 to 3 decades, but they've mostly been limited to a laboratory characterization tool. This is one example of a fiber optic sensor. It's a fiber Bragg grating, and the way it works is that you functionalize a fiber optic cable over a small length by changing its refractive index in a periodically modulated manner. And what that does is it makes it sensitive to certain design wavelength of the broadband light that comes into the fiber optic cable. And this can be used to monitor a number of different parameters ranging from strain, temperature, chemical composition, to even current and voltage. All of these parameters are of course useful for cell state estimation in batteries. What it happens is that these stimuli typically tend to shift the wavelength that's reflected by the sensor, and by monitoring that wavelength shift, you can measure these parameters with very high accuracy. The other nice thing about these sensors is that you can multiplex, so you can have multiple sensors along the same hair-thin cable that are sensitive to different wavelength slices of your spectrum. And people have demonstrated as many as 50 to 100 sensors on that same hair-thin fiber optic cable. This is very useful for monitoring a large area and doing distributed sensing, especially in battery packs. And of course, these are made of glass or plastic, so they're inherently very lightweight. They are based on light propagating in the fiber, so they're inherently immune to electromagnetic interference and electrostatic discharge. And by using the right materials, you can make this to be very robust to a number of harsh environments, as has been demonstrated in other challenging applications. So all of these properties make it very intriguing for the use case of battery management systems. And in particular, in this project, we had this broad goal of wanting to embed inside the battery cells. We did successfully achieve that collaborating with LG Chem Power and have built XEV grade cells, as I'll explain later. But on our way to that point, we had several development iterations to go through. So we kind of started out with this lower hanging fruit of externally mounted sensors, and this shows a picture of an early study in that respect. So this has a large format pouch cell with two sensors, one monitoring strain, with the other monitoring temperature. And we did simulate the module level effects even in these cell level studies by putting them under pressure and thermal management system, so that what we got at the cell level was still somewhat representative of what you'll see in the module under pressure. The initial results from these were intriguing enough that this whole took a life of its own. We got repeatable strain signals across a number of different strain rates. I show plots from C/5 to 2/3, but we pushed this up to 1.5 C and seen similar results, both for the charge and discharge. And we also saw similar results for the dynamic cycles that we exercised it through. So this raises the possibility that you can train your algorithms on a few static curves and have that be applicable across a broad range of dynamic cycles and other use cases. And there's been a number of interesting features that we've been able to detect in all these strain curves. One example of that is if you take the first derivative of the signal, you'll notice that there's some very distinctive peaks in the signal that happen at the same SOC levels for these initial cycles, regardless of the charge or discharge rate. We proved from subsequent analysis that these actually correspond to the intercalation stage transition points that a cell goes through as it goes through charge and discharge cycle. So a graphite electrode typically goes through 4 of these, as is well known in the literature, as you go from 0% state of charge to 100% state of charge. And so every time it undergoes one of these stage transitions, you see a sharp spike in the strain signal. And it's also known in the literature from careful laboratory studies using some pretty intricate equipment that these stages actually drift over the course of the life in a very distinctive pattern. So now that you're able to monitor this with a solution that can be fieldable, you can imagine using this on the field to track cells' life and its aging over the course of the operation. One of the known pain points for battery management systems today is their operation in cold temperatures. I think there's been enough media reports about that and how EV drivers feel so much more standard in cold temperatures. So I won't go into too much detail of that, but we wanted to put our own sensors through this acid test. And so here's an example of a test that we did at minus 15 degrees Celsius. We put the cell through its known limits of operational conditions. So we put it through the lowest cell terminal voltage to the highest cell terminal voltage at the maximum charge and discharge rates recommended by our battery manufacturer LG. So the maximum rates in this case were C/10 for the charge and C/2 for the discharge. And here's what the fiber optic signal looks like. Before I go into that, I should mention that even though we cycled the cell through its known cell terminal voltage limits, when you Coulomb counted this, this depth of discharge was only about 50% compared to what you can achieve at room temperature. Now, if you look at the fiber optic signal, the peak strain that we achieved at the end of the charge was about half the amplitude of the full strain at room temperature. So this suggests that our fiber optic signal was accurately picking up the right state of charge even on this cold test. And it's pretty repeatable across the multiple cycles that we exercised it through. And for the external sensing use case, one might argue that you can as well do it with electrical sensors. Apart from the disadvantages that I already mentioned in terms of the heavier cabling and the sensitivity to electromagnetic interference, in our initial tests with electrical foil strain gauges, we saw that the strain signal was nowhere as repeatable as the fiber optic strain signal, which is plotted in black here. And similarly for NTC thermistors, we saw that we were picking up a fair amount of electromagnetic interference, even in our controlled laboratory conditions. And this only, of course, gets much worse as you put it in the fielded use case. Now, of course, going beyond external sensing to actually embedding the fibers in the cell, there is no real competition from the electrical sensors. I've heard of some people doing it, but they come up with all kinds of fancy ideas to protect the cables so that they don't mess with the cell performance. Then it just becomes being this humongous electrical cable that's going in the cell. But with fiber optic sensors, because they're inherently immune to electrostatic discharge and EMI, you don't need any protection. You just put it in there with the regular coating that goes on top of it. And as I said, this is one example of how we embedded it inside the cell. But to get to this point, we had to go through a fair number of development iterations, and I can show you 10 different configurations that didn't quite work before we got to this point. But once we achieved this, we were able to consistently make fiber optic sensor embedded cells, and we recently transitioned this to large format pouch cells that are used in EVs today by LG. So I think in retrospect, this development process was well worth it, because when we looked at the signals coming from inside the cells, they just blew us away. The strain signals were 2 to 5 times stronger from the internal cell than it was from what you could monitor on the cell skin. And now that you have the ability to monitor inside the cell, you can directly monitor the electrode temperature as well. This is going to get increasingly important as the industry transitions to larger cells with thicker formats. There have been numerical simulations reported in the literature that have indicated as much as a 20 degrees difference between the internal electrode temperature and the external skin temperature. So now you have the opportunity to directly monitor that. And there's some DOE labs that have reached out to us with interest in doing more careful characterization using these fiber optic sensors. There is also a number of other cell state features that are detectable, and I'll talk about some of them in the coming slides here. But beyond static cycles in the real world field use case, you really care more about dynamic cycles, because that's, EVs are never static, they're constantly changing conditions. And towards that, we started doing dynamic cycles with these internal sensors. Here's one example of an initial test. It's a relatively mild dynamic cycle. So if you look at that SOC variation over time, it's almost static. But now look at the current signal and you convince yourself that it is indeed a dynamic cycle, albeit a very mild one. Look at the voltage signal for this same use case. Even for this relatively mild dynamic cycle, the cell voltage is all over the map, and it gets much uglier as you go to 0% state of charge. And then when you go to more aggressive dynamic cycles, as is typical for EVs, that cell voltage is just all over the map. And I really developed a healthy respect and sympathy for all the BMS algorithms engineers who are using voltage signals today for EVs. Now look at the fiber optic signals for the same cycle, and look at how much more stable and robust those fiber optic signals are for that same dynamic cycle. I plot the internal signal in blue and the external signal in red for that same cell. It's also apparent from this plot how much stronger the internal signal is compared to the external signal. The other point to note is that the internal signal is also more robust to these dynamic oscillations than the external one is. So the next step was to see whether this continued to hold true for the large format cells, in particular when we put them together in a module under pressure and with thermal management systems. So here we put together 4 of those large format cells with the embedded sensors into a module. This is a commercial LG module that goes into EVs today. And we had to make only minor modifications to the module to accommodate the fiber optics cables exiting the cells. And these should not affect the mass manufacturing process and increase the cost point significantly. And the signals from these continued to look very promising. One of the key tests we started off with was the hybrid pulse power characterization test. This might be familiar to those of you who do EV testing, but for those of you who don't, the plot below just shows you what kind of signal this looks like. So it starts with a short 10-second 7C discharge pulse, followed by a rest phase, and then a 5C charge, and then another minute's rest. Look at the strain signals coming from the fiber optic sensors inside the cell. When we showed this to EV OEM engineers, this is what they call the most ideal HPPC response, because you can see that the strain changes linearly over the charge and discharge pulse, and then when it's resting, it's perfectly flat. it wasn't surprising to us after seeing these results that even for the most aggressive dynamic cycles, such as UDDS and US06, where there's changes in the direction of the current pretty much every second or every millisecond, the strain curves from the dynamic cycles for the strain were pretty much aligned well with the static cycles. And so you can continue doing what I was telling you earlier, where you train the algorithms with a few static cycles and have it be applicable across the most aggressive dynamic cycles. And this is validated further with the US06 cycle, which is one of the most aggressive use case scenarios for XCVs today. So using these strain curves, we were able to develop algorithms that were giving us SOC accuracies of 2.5% or better, or a very wide SOC range, 5 to 100%, and I think there's room for further improvement in the 0 to 5% SOC range with further development. This is a factor of 2 times or better over the state of the art, but there's some debate in the industry as to what that exact factor is, so I won't get into that debate here. But I think everyone in the industry agrees that these are really exciting curves. And we also done tests where we tried to see if we could get parameters that were indicative of state of health. And so this is one example of a test that we did with that module, where we put the module through pretty aggressive cycles to induce capacity fade. And you can see that we were able to detect features on the plot on the left that correlated pretty well with the capacity fade. And using this feature, we were able to predict capacity ahead of time, capacity fade ahead of time, just knowing the initial capacity in the fiber optic signal at a given point with 2.2% or better accuracy with a 10 cycle window. And that accuracy gets better and better as you go to smaller windows of prediction. We've also been able to detect features that are indicative of cell failures. In particular, we had some preliminary tests where we saw that we were detecting some lithium plating indicators before the cell actually failed. But those are preliminary results that need to be verified further, and we are planning to do further validation tests on that. Now, of course, this has excited a lot of the industry OEM engineers, but then they start asking us the questions about how this might eventually become field deployable. And in that respect, we've done a fair number of tests already in the ARPA-E project. One of the key questions that come up is that if you embed the fiber in the cell, will that cause the cell to fail faster? And we did put the cells through stress tests that indicate that the capacity degradation is pretty much consistent with the cells that don't have the fiber from that same line. And we projected that you can have a cell with the fiber optic sensor that's more than 1,100 cycles. And that is a key USO ABC metric, about 1,000 cycles for the cell to be EV grade. And the question we get is that, are the fiber optics going to be stable in the cell over a long period of time? And so in that respect, we've done stress tests where we put the fiber optic sensor with different coatings in an electrolyte solution and just checked its drift over the course of the life. There were some coatings that failed this test about 20-30 weeks into the test, but there are others that survived this for 60 weeks and still counting. This is an ongoing test presently. And we have also done tests at LG that confirm that the seal integrity can be very comparable whether you embed the fiber optic cable or not if you embed it in the right way that we've developed. A key enabler to make this happen, as I mentioned, was reducing the cost and size of the fiber optic readout unit. And so in that respect, a key advance we made at PARC is develop this aggressively multiplexed readout, building on our initial technology that can monitor hundreds of channels in the small form factor, which can get even smaller with further development. And this actually pushes the envelope in terms of the resolution achievable for fiber optic sensing. We were able to demonstrate about 50 femtometers as resolution, which is about 20 times better than the state of the art, which is about 1 picometer of resolution. And the cost points, we've done the analysis not just for the readout, but also the whole system, including the fiber optic sensors and other balance of system components. And we proved that it can drop to a few $100, and that cost point can drop further over time thanks to the Moore's law for photonics ICs. So with all these developments, having fiber optic sensors that can monitor cell state so much more accurately, and having a readout system that's compact and field deployable and can be mass produced at a very reasonable cost point, we envision that this sensor solution can eventually displace the electrical sensing on BMS today. And towards that vision, we did the actual cost performance analysis of what that would translate in terms of the savings by replacing all the electrical sensors and putting fiber optic sensors. So this is an estimate for the 2011 Chevy board for which we had teardown data. We've also done this analysis for about 4 or 5 other EVs that we had access to the teardown data. For this particular Chevy board configuration, we assumed that we were monitoring one of the 3 parallel strings. So about 96 cells monitored, and the whole system costs only about $294, and we're saving about $850 on the Chevy board thanks to this. And of course, the fiber optic sensing system is much lighter than the electrical sensing, so you're also gaining some benefits in terms of lightweighting. The second scenario I'm showing here is for the same battery pack, if I monitor every single cell by embedding the fibers inside, so that's a factor of 3 times more sensors, the cost has only gone up by about $30. And that's because you can take advantage of the multiplexing capabilities of the fiber optic sensing system. You don't need a lot more components to monitor a much higher number of sensors. So the value proposition of this technology is only going to get better and better as you go to larger and larger packs like grid storage and other advanced applications. So in summary, in this presentation, I talked about how we put a brand new sensing option on the table in terms of fiber optic sensing, and I showed how those can enable you to get very high accuracy state of charge and state of health estimation. And I also showed you some glimpses on how we're making this field deployable and practical using our low-cost compact readout developed at PARC that's pushed the envelope in terms of what you can achieve with fiber optic sensing. And also some summary results from the cost performance analysis that indicate that this can be very competitive with electrical sensing and eventually replace them altogether. So I'm excited to announce that at this stage we had a number of OEMs who are interested in engaging with us, and one particular major OEM here in Michigan is going to take this into their lab and start evaluating this in a lot more detail over the next 6 to 12 months. So that will be a more serious acid test under a broader range of operational scenarios that we'll be putting our technology through. If you're interested in similarly evaluating sensor, please come talk to me. That's my email, and we also have a booth here, booth number 1954, where we have some of the prototypes that I talked about in this talk today. So that's all I had, and I'll pause to see if there are any questions at this point. Thank you. Please come up to the mic.
What's the communication interface you have on the readout device?
So that's a good question, and that's one of the major advantages of fiber optic sensing is that the same cable that's used for sensing is also used as the communications bus, right? So it's just the same light signal going back to the fiber optic readout, and then that's converting that to a digital electronic signal, and you can have the BMS right on that same readout.
So the readout device doesn't provide that digital electronic circuit?
Not in the present prototype, but it's a very easy step to take that and put that on there. That's been already solved in the industry, so we didn't tackle that particular problem yet.
Thank you.
Sure. Any other questions?
Yes, the state of charge correlation to the wavelength shift, is that the same for all batteries, or do you have to characterize each individual battery for that curve?
Good question. So I would say that we've cycled built about 8 to 10 fiber optic embedded cells, and we found that the strain curves are very similar to each other, especially for that internal sensing configuration. I won't say they're identical yet just because we build those cells by hand in a research test line, but I'm pretty optimistic that if you build that in a controlled manner using some kind of machine, that the signal should be more and more repeatable. Thank you.
Have you tested any of these under vibration conditions or anything like that?
Yeah, we have. We've done initial vibration tests. It was a relatively small shaker table in our lab, so we kind of did component-wise vibration tests. But I mentioned that OEM testing that's about to start. There we're planning to take a large module with the whole system and put it through a much bigger shaker. So that'll be a more serious acid test. But the initial results from our lab tests indicate that it should be feasible, quite feasible, to make it vibration robust. Last call for questions. Okay. Well, thank you again.